Good afternoon, everyone. My name is Justin Essery. I'm an associate professor here at Wake Forest University. Welcome to the International Methods Colloquium. The IMC is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and also sponsored by Springer Publishing. This week's presenter is Cameron Wimpy of the Department of Political Science at Arkansas State University, giving a talk entitled On the Interpretation and Application of Spatial Regression Models in Political Science. Cameron's talk is going to last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question at any time using the Zoom Q&A button that appears at the bottom of your webinar window. You can ask a question any time, but I'm going to hold all the questions till the end of the presentation. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box and we can unmute you. Otherwise, I will read your question aloud during the Q&A period. A link to Cameron's slides and paper will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation. Now I'd like to welcome Cameron Wimpy to the IMC. Welcome, Cameron.
Thanks, Justin. So before I get started, I just want to acknowledge that the work here that I'm presenting is based on two recent papers, one that just appeared in Political Science Research and Methods, and another one coming out in the Journal of Politics. And both papers are co-authored with Larry Williams and Guy Whitten. And so I want to acknowledge that from the outset, that I'm presenting from those papers that I co-authored, but this is just me on this presentation. And it's worth noting, if there are mistakes here, it's probably something I'm making in the presentation and not something that reflects on them. So based on that, I'm dividing things up here into two sections, one focused on one of the papers, the other on the other paper. And really, this comes out of some work we've been doing for the past several years, looking at the application of spatial models in political science. And it's no secret, there's been an increase in these types of models. We certainly welcome that and have been part of that. And so the parts that we think are missing to some degree are the ability for applied researchers to get up and running with spatial econometric or spatial regression models quite easily. That's a challenge for applied researchers. For many people here, it may not be a challenge, and so that's also worth keeping in mind as I go through this. But also the interpretation of these models is somewhat lagging. Often what we see are people running the models, estimating the models, and then under-interpreting the results, just looking at coefficients and not moving on from there. And so that's how we're going to proceed. There are a few basic assumptions I'm making. First off, I'm assuming most folks watching are probably somewhat familiar with the idea of spatial models. If not, obviously, there are some things here that may go past you a little bit, although I'm trying to keep it as accessible as possible. So I'll lay a bit of the groundwork for those that don't know. But again, I'm assuming most people have some familiarity with at least the idea. And that's to say, at a basic level, what we're talking about here is some type of interdependence among our units of analysis. That's either something that we need to take care of in our modeling process so we can get accurate estimates and uncertainty estimates of those things we're interested in, or something we actually want to theorize and model with respect to those spatial processes. And so I think that's something most of us are at least probably familiar with a little bit. Second, in general, it's worth pointing out that we're also following in some large footsteps, not just in political science, but from other disciplines, certainly geography, regional science, economics, and so on. But what we're doing here is trying to incrementally add to what's been done before. So it's worth acknowledging some of these things that have come before us. So certainly we're playing by some basic rules with respect to things like Galton's problem, which is understanding the process underlying spatial correlations. Tobler's first law of geography, saying that things that are nearer to each other are more related than things that are further away. And then certainly the political science editions of Beck et al. Saying space is more than geography. So everything I talk about here, to the extent that I use examples, if they're geographic, just know we fully admit that these examples are geographic, but certainly space need not only apply to geography, and we're on board with that. And certainly my co-authors have demonstrated that elsewhere. And then finally, some of the work of Francaise and Hayes, and that is that spatial dependence or spatial interdependence is substance, not a nuisance, so model it. And the idea there is, if we're seeing interactions between our units of analysis, then maybe we should theorize and model what that interaction is rather than just trying to wash it out or get rid of it and look at things in isolation. So I just wanted to acknowledge those are some of the rules by which I'm playing here. So we've presented this before elsewhere, but I think it's worth pointing out that this comes from some work of J. Paul Elhorst and colleagues that puts together a taxonomy of spatial models. And so starting out here with what they call a general nesting spatial model and moving on to some various directions. One will be going to the top, a spatial autocorrelation model, where we have spatial processes both in the outcomes and in the unobserved error process, a spatial Durbin model where we have spatial dependence in the outcome and in the observable predictive variables, and then a spatial Durbin model, a spatial Durbin error model, where we just have spatial dependence in the observable predictors, but also in the unobserved error process. And from there, we can collapse down a bit to the spatial lag model, which is probably the model most people are most familiar with, also known as spatial autoregressive model or SAR model. Then we have the spatial X model, which is part of what I'm talking about today, where we just have spatial interactions in the on the right-hand side in the predictive variables, and then the spatial error model, which is akin to something where we're trying to wash out the spatial process and look at things in isolation, not unlike what we might do with, panel corrected standard errors or things of that nature. And finally, it's worth pointing out in all these cases, if we have no spatial dependence, we just collapse back down to a typical linear model. And so that's the framework that Elhorst put together, and I think it's quite useful for visualizing how all these spatial models fit together. Cook, Francaise, and Hayes have done something similar with a typology in tabular format, putting some of these models out there, and I think that's worth looking at as well. But if we think more about how many of us start when it comes to doing applied research in political science, it's often the case that we start with something that's more akin to thinking about a basic model and work up when we're building our theories into complexity from there. And so perhaps we may just want to do something where we wash out any spatial connections and get back to our units of interest. And that's, again, what we're most commonly seeing for a long time. Or perhaps we want to move into these models that we see most often in political science with the spatial lag model or the spatial X model. And that's where the focus, I'm just saying, is going to be for today. These two models and how they relate to what we might normally do. It's certainly worth pointing out that issues are abound with not doing examining any spatial interactions in your work. So obviously you're ignoring potentially any substantive spatial interpretations. There are problems with respect to admitted variable bias, bias in the estimation process, wrong estimates, wrong signs, wrong standard errors, a bad fit. So there are many things that can happen from ignoring any spatial patterns in your data. So if anything else, I would just suggest that you consider that as we go through this. So real quick, for those who have no exposure to this, I'm just going to point out what's probably the newest part of these models for you. And I'm not going to spend a lot of time here because I'm assuming most people have seen this, but it's this W matrix or a spatial weights matrix. But what goes in there, obviously this might be somewhat controversial to some people, but we would suggest it's typically whatever your theory dictates, that the weights matrix should be theory driven. And the weights matrix, I should just say on those previous slides, is just denoted by W, but that's the matrix that determines the degree of connectivity between units. And so have a simple example here. We can take a simple contiguity matrix between three observations, and I'll just put it here. And so here what we have, units 1 and 2 and 2 and 3 are neighbors, but units 1 and 3 are not. And so in this case, it's simple contiguity. We're just using ones and zeros. You get a 1 if you're a neighbor, a 0 if you're not. And this is the part of the model that determines, again, the degree to which units are connected spatially. And you can obviously put together these matrices any number of ways. That's not what my focus is on here. We're trying to keep things as simple as possible when it comes to the weights matrix, but I do want to just kind of outline this is what we're talking about in most cases. The matrix can be row standardized or not, and that just simply means I'll show you in a second what that means. But that, whether or not you do that, we typically follow Plupper and Neumeier and suggest that depends on your theory. But that looks something like this, where you're just taking an average across the row and getting an average degree of spatial dependence for all neighbors of a given unit. And this is the formula for that. But if you're really interested in this, there are other places to look as well, but I would certainly refer you to the Newmeyer and Plupper 2016 paper just called W in Political Science Research and Methods, where they say the importance of W stands in stark contrast to applied researchers typically employing crude proxy variables for true connectivity, such as geographical proximity, and adopting standard modeling convention for specifying W rather than substantive theory. All that's to say that W should be theory-driven. There's probably different ways to connect units spatially beyond geography, and so that's all things worth considering. But I'm not going to spend much more time on the W matrix specifically. Certainly happy to talk about it if anyone doesn't understand or is curious about this interpretation of things. Okay, so starting here with the spatial lag model, or the SAR model, spatial autoregressive model. It's known by many names. This is what it looks like in basic form. So here, Y is just our vector of observations on the dependent variable. X is a matrix of exogenous explanatory variables, however large it needs to be, with typical parameter estimates in the form of betas here. W is the spatial weights matrix I just introduced you to if you've not seen it before. And again, that's what determines the degree of connectivity between units. Rho here is the coefficient indicating the average degree of spatial dependence between units. And so this is a global measure of spatial dependence. And when I say global, I don't necessarily mean global as in the geographic world or however you might describe it, but global meaning all units that you're examining. And so something that you think impacts every unit in your study. And of course, we have our error term. It's also worth looking at this in a reduced form just to isolate the endogenous component of the model. And here I is just an n by n identity matrix. And together, when you subtract the rho W inverse here, so the part here with the coefficient that I just mentioned for the global spatial average, and if you subtract that and the weights matrix, this represents what we call the spatial multiplier. And this, of course, plays a huge filtering role in these models. And this will become clear in a second, but certainly it's a big part of this process, and it's part of the problems with using SAR models in general. And it's something that we would argue a number of applied researchers certainly haven't realized in the process of conducting their work, and something that we think is really important to raise here. And so I think just real quick, though, before I move any further, I want to make sure that folks are understanding that I'm not being too critical of the SAR model as a way of going about modeling some spatial theory. If your spatial theory calls for a SAR model, if your spatial theory is global in nature, and you have a theory about how some spatial shock in a unit of analysis impacts every unit in your data set, or every unit you care about, then it's not a problem. But there are some things, as we'll see later, about that are implied in the SAR process, whether folks realize it or not. And there's some things about interpreting SAR models that becomes very important. But this is not just a wholesale critique of the SAR model. And certainly there are those out there, and they may be worth looking at. But we just think the SAR model is a fairly complex model to start with. And so that's the main point here. It can be hard to estimate, difficult to interpret, and again, probably not the best place to start for many political science applications. And so if we break things down a little bit, most of the time we're theorizing and modeling first order relationships. And so, and I say that to mean broadly, folks who are interested in examining these types of models in political science, it's often the case, and we see this in a review of the literature that we do, that folks are most interested in modeling things that are happening nearby. So things that are influenced by a neighbor of the unit of analysis, and so on, and not a neighbor of a neighbor of a neighbor, something way down some type of network. Now, of course, there are folks who are interested in broader types of network analysis and that sort of thing, and this really is distinct from that. So I want to make that clear too. So one well-established property of the SAR model, again, is that it implicitly models higher order spatial effects or spatial relationships, because the spatial multiplier expands like this. And so what you see in this expansion, and this is an infinite series expansion, this goes all the way through your entire network. And when you look at this in matrix form, which we'll do in a second, you'll see how this compounds in a problematic way relative to most theories that you see in the literature. Okay, so if we start here again with that same series, we look at just a couple of examples. So we have a simple weights matrix here, where the one I showed earlier, where units 1 and 2 and 2 and 3 are connected, but 1 and 3 are not. We might expect weak second order relationships, and this is a sort of a true, so that the first one here is a first order relationship. The second one is a second order relationship. So something happening in a neighbor of a neighbor that may have an impact on the unit of analysis. And there's ways to capture this in other types of spatial models, but it's not easily captured this way. But what's happening here in this squared matrix is just the second part of this infinite series expansion. And you can see immediately what's happening are what are known as feedback effects, where something happens in a unit of analysis, some sort of shock, it goes to a neighbor and feeds back on the unit of analysis. And so here you have that squared matrix, and you can see what that looks like. Again, this ends up being a fairly restrictive common factor assumption that assumes that each x is linked to y in an identical level of spatial autocorrelation. So, and this is probably highly unrealistic in practice, and I don't think that's a controversial thing to say. And this is something that's happening in the SAR process, whether people realize it or not. Now, I know many people are familiar with this, but what you continue to see in the literature is estimating this model and not accounting for this part of the process and not mapping that back onto a theory. So if we start with a theory about some spatial process, and that theory is about a fairly local spatial process, if you estimate a SAR model and you do nothing to account for the way the SAR model is involving every unit in the analysis this way, you're probably missing a big part of the puzzle. Okay, so this is a basic example from the paper that is coming out in the JOP, but it's a little bit more involved than those simpler examples I just showed. So we have here a basic map that we put together and 3 different matrices, one just being the first order neighbors, the second one being first order neighbors squared, so which is that second part of that infinite series, and then true second order neighbors. And so it may be the case that we're interested in something that is an order or 2 or 3 away from the unit of analysis, and how that may affect our unit of analysis. And this matrix on the right gives a start to how you might think about that. But the second one is the one that becomes problematic quite quickly when you start to see how things show up in this infinite series expansion, and whether or not your theory is really accounting for the spatial dependence to be playing out in the network that way. Okay, so this paper in the JOP called XMark the Spot, again, it's coming out pretty soon. But what we're doing here is introducing to political science, and we're not the first ones to introduce it, but certainly we're trying to build on what others have done and expand on what others have done to make a case for the spatial X model is a good starting point for a lot of spatial theories and modeling efforts in political science. So again, showed this earlier, but here the main thing to look at that might be new to you is this the W matrix, and here Z is our some weighted predictor variable where we're weighting some process from neighbors on the unit of analysis, and theta is just going to be our coefficient that we use to interpret the spatial X model. And again, we can have more than one explanatory variable weighted with the same weights matrix. We could use different weights matrices, but what you can see is we don't have that endogenous component. The complexity here is far reduced. And if I don't say it later, it's worth pointing out that, and I'm sure again many people know this, but to estimate this model, we just need whatever kind of model you're used to estimating. So you can just OLS model, logit model, what ordered logit, whatever it is you're interested in using, and simply weighting our predictors as needed. In the SAR model, that's not the case. We have a variety of reasons why we need to use more complex estimation algorithms for the SAR model, and many of you who've gotten into complex spatial models probably know this. And it becomes much more difficult for an applied researcher to get up and running with a SAR model than it would be in this case. Of course, you still have to do the weighting of the variables, so multiplying some weights matrix, specifying the weights matrix, multiplying it by your variables of interest. That process doesn't go away, but the complex estimation process does. So it's worth pointing that out. But again, this is not really what we're focused on here. Okay, so some advantages of the SLX. In contrast with the SAR, we can estimate the SLX via OLS, as I just said. The X and Z can be the same or different. We can put a different parameter for the spatial parameter on any number of predictive variables that we want. Higher order effects can easily be modeled if we want to. And these are, true higher order effects. So we can model the impact of a second order effect or a third order effect as needed, just by specifying them directly. We can also, if we're interested in estimating feedback effects, we can do that too. But again, by specifying it directly rather than automatically as part of the process when it's probably not theorized. So relative to the SAR model, this is a huge upside in terms of flexibility. So it's a very flexible modeling framework. Again, you can use the types of models that you're used to using. The estimates are relatively easy to interpret, as we'll show in a little bit. And certainly some of the work we're doing in the future and some of the work you can see in the supplemental materials of this JLP article when it comes out, we start to look at how the SLX much more easily fits in with modeling temporal processes along with spatial processes compared to the SAR. Now, again, that's not to say there's not a place for the SAR or a spatial Durbin model or a spatial error model or anything else, and also involving time. But if you're just trying to start simple and get more complex from there, this is a much more flexible and easier place to start. Okay, so this is just a table from the paper where we're looking at what people have done, but it's worth pointing out, I don't want to spend a lot of time here because you can just see it in the table, but relatively few papers went along and explicitly specified theories that were global in nature when they used SAR models. So in many cases, they may have been estimating something that was global in nature, but they explicitly they were not explicit about what their intentions were, or seemed to not really grasp the point that a SAR model implies that theoretically you're thinking about something that is global in nature and not local. And so that's one of the major findings there. There is some use of the SLX in political science, although certainly in many cases folks are using SLX without saying they're using SLX, which is fine, but the interpretation ends up being a bit lagging in some cases. But it's all to say that what you see doing literature surveys is, I wouldn't say troubling, but certainly many people are not going as far as they could, or at least making it clear that they understand the implications of the model they're using relative to their theory. And so what we did here was just some selected results from this, because we don't have time to go into everything we did. But what we did here was look at the recovery rates for a variety of SLX specifications for the SAR DGP. So what we did was we set up a SAR DGP. We're using the SLX to see how well it does in the case of a SAR DGP. So because one critique of this might be that, okay, the SLX is great, or Spatial X is great for something that is Spatial X in nature in terms of the actual spatial process. But if something is playing out globally, then obviously the SAR is a better choice. Now, while we would certainly agree with that if the researcher understands what's happening, in many cases we don't. And in many cases, what we see here is the SLX is quite adept at recovering these effects from a SAR DGP. And really what we see is in this top section for everything but the most extreme cases of spatial dependence. And what you see across the top row there is just varying the row from negative 0.8 to positive 0.8 across these different experiments. And you see a pretty good job here overall. This is a very simplistic SLX estimation. It's the most basic model. And so while it's doing a pretty good job, we have lower levels a spatial dependence, which incidentally is what you most often see looking at the literature again. You see spatial effects everywhere, to be sure, but the actual degree of spatial dependence is often quite low. And so the SLX in that area does a really good job. When you get to the more extreme areas of a SAR process using a simple SLX model, it doesn't do that great of a job, and I think that's what we would expect. But the question becomes, to what extent can we eliminate these concerns by adding a bit of additional complexity? And really what we're thinking about is theoretically specified direct changes to the model rather than it doing it for us. So in the second set of experiments here, what we do is we add a first order weights matrix squared and an additional SLX coefficient. And what we see here, a much better recovery rate. So again, if you have a clear theoretical idea rather of the spatial process, you can specify it directly using this SLX framework and get close to 95% recovery in our experiments. And then finally, in the third set, we get even more complicated with a cubed matrix, and we do even better. But it's worth pointing out, as you might suspect, when you get into this arena, you start to get a fair amount of multicollinearity and so on. So you know, that's something that has to be considered, dealt with. I don't think it means that you should not consider it in that case, but you're getting into a fairly complex theory, I would assume, if you're specifying all of those things. This is just an example to see how extreme you can get with the SLX and capture what's happening with the SAR. Now here we have just a series of graphs where we're assessing the performance of the SAR in an SLX process. And what we see, the basic question we're asking is, how do the models perform when the data are generated in a manner consistent with the SLX? And what we're looking at, again, is trying to recover the true average direct and indirect effects that we've built into this. And we calculate it via the approach I'll talk about in a minute. So the SAR, what you can see is doesn't do that well in the degree of what we call spatial heterogeneity. And so when you have situations in which you've specified multiple predictor variables with multiple types of spatial connectivity, the SAR is not able to pick that up in a way that is nearly as good as the SLX does the reverse of that process. And I'm happy to dig into this a bit more if someone's interested in terms of how all we got there. But the basic point is we're able to recover things much more nicely using the SLX on a SAR framework than we are with a SAR on the SLX framework, which seems like it would be the immediate critique. Might be the reverse of that if you were thinking about why the SLX might be a bad idea. And so that was obviously somewhat surprising to us, but it's a little bit less surprising when you start to think about the way spatial profiles can vary across observations. And again, this idea of what we call in the paper spatial heterogeneity, which is different spatial processes playing out different ways from different units via different types of connectivity. The SAR, again, you can estimate different matrices in the SAR and try to build something like that, but the complexity of that is such that it's not at all easy to interpret. And you might be able to get a couple of different estimates of those row global coefficients and get this average degree of dependence across whatever group of data you're looking at, but you're not going to end up in a place where you can get clear effects and point out something that is much more substantively interesting to any reader of your work. So we have an applied example in the paper, and I'm looking at my time and I don't want to spend a lot of time here, but I'll say we put together an applied example of looking at defense burdens, which is defense spending as a percent of GDP. And what we ultimately did was started looking at a variety of ways in which spatial processes can play out, and using the SAR model to estimate things, again, globally to see what you get, and then comparing that to a variety of, as you can see here, different spatial X configurations. So using contiguity, in different types of wars, using whether or not these countries were allies in wars and how that affects their defense spending. And then at the bottom, you just have a bunch of non-spatial estimates, which are probably not interesting unless you're interested in this literature specifically. But what we see is the SAR, obviously you're getting something there, which is that global average of spatial dependence, but you're not able to get these direct effects in a way that you can specify things across that different spatial profile with different types of spatial heterogeneity. And so I'll just say, well, if anyone's interested more in this, we can come back and go through each one individually, but I want to spend enough time for the second part here. So just to say, kind of wrapping up what we did here, and I certainly encourage you to look at the paper because it probably explains some of this better than I did. But first, researchers should carefully consider the nature of spatial dependence in their theories and choose a model that best reflects the expectations of how these processes work. Second, unless their theories are about global dependence among outcomes, they should start with a simple SLX model, work from there towards a more complex model and specifications as appropriate. Third, when researchers suspect that spatial diffusion processes are heterogeneous, so again, that's the idea of spatial heterogeneity, researchers should employ the SLX with varied specifications of matrices based on these expectations. Again, you can do something similar in a SAR framework, but interpretation and estimation becomes much more complex. And fourth, researchers should move beyond a cursory discussion of the direction and significance of the spatial parameters to an interpretation of all the estimated effects, so direct, indirect, and total effects, which accounts for what some people might call the pre-spatial, post-spatial, and everything added together effects for the analysis. Because what you most often see, again, in reviewing the literature is just estimating a spatial model and looking at the global coefficient and saying there's a spatial process here, it's positive and significant, and leaving it at that, and not really going into any degree of substance or any degree of interpretation of the other X variables. And in many cases, with the SAR model, the other X variables don't matter much anyway because of that common factor restriction, which I talked about earlier. Okay, so the other paper, this is the one that just came out in Political Science Research and Methods, just putting the title here in case you want to go find it. What we did here, again, looking at a survey of the literature, the use of these models in political science to look at things. So we identified, in this case, 155 published works that we looked at. Of those, where they cited two seminal spatial articles. So the Beck Spaces More Than Geography, and then the Frances and Hayes 2007 piece. So of those 155, 94 estimated actual spatial models, and 60% of those reported results from a SAR model. And so what you see when you start looking at the results, especially from SAR models, are two troubling patterns concerning interpretation the quantities of interest. So first, researchers mostly ignore that simultaneous endogenous nature of the SAR specification when they interpret the models. So typically they just they interpret any coefficients as though they're regular OLS coefficients, don't consider the fact that they're all being filtered spatially, whether or not that's clear, but it certainly should be clear from that earlier point on the infinite series expansion and the spatial multiplier. That fail to acknowledge any higher order effects that are there implicitly, whether they realize it or not, and with a few exceptions, don't do anything to interpret the spatial effects beyond, again, an assessment and of the direction and significance of the spatial parameter. And only about 15% of the papers provide any sort of graphical depiction of the spatial process. So what we say here, interpreting the estimated causal effects of spatial econometric models requires carefully incorporating the impact of the covariates, the strength of the spatial dependence, and the spatial profile of each observation. That's all to say that there's a number of things that have to be accounted for when it comes to interpretation of spatial models. You can't just stop at interpreting the sign and significance of the spatial parameter. You have to go on and understand the filtering that's being done and understand that there are ways to use the data you have to get more meaningful and substantive interpretations. And so what we provide in the paper are here just two examples of the partitioning of effects in both the SAR model on top here and the partitioning of effects in the Spatial X model on the bottom table here, and how you can go about doing that using the parameters that you have. And and this provides a roadmap. And in the paper, we provide a number of just, again, really small examples of seeing how these processes play out. But in essence, what you're doing is using what you have to put together a partial derivatives matrix from which you can then get things more akin to marginal effects and things that we might be interested in that account for space or not, depending on what your interest is. Okay, so we have an applied example here, just again, a fairly basic example, in this case, using wealth and democracy. We are certainly not calling this some sort of overarching piece on this topic. In particular, we're not building any time component into this. We're just using data from 1994 and using Freedom House's 14-point democracy score, and that's reversed. So just for interpretation purposes, and then log GDP per capita. So again, we're just using 1994 to make this as simple as possible, and we are using spatial contiguity or geographic contiguity rather, just again for ease of interpretation, but fully admitting you could do something different. Okay, so and there's some other things about the modeling process I could talk about, but certainly it's a fairly simplistic model based on this basic theory. And the initial results here, so what we've done, put together some initial results that you might get from estimating this kind of model using both a SAR process and then a variety of spatial X specifications. So SAR on the left, spatial X on the right. So 4 models here presenting the impact of wealth on democracy. The SAR model follows a simple specification with a geographic weights matrix. The SLX models include those higher order effects that we talked about earlier. And so what becomes more interesting, though, is to then start to break these out into what are known as total, direct, and indirect effects. And so in the paper, we provide the actual process of how you get to this point. And certainly some of the software that you see these days provides some help on this. Certainly Stata is getting close to that, but at least for the SAR model, in certain types of ways of estimating the SAR model, not for the SLX model, but it's pretty easy to get there with the SLX. But what we can see here are looking at the combined effects of both pre-spatial and spatial, and then looking at the spatial effects and the pre-spatial effects all separately, kind of like marginal effects, to see what the impacts are of wealth and democracy across these variety of spatial specifications. Now, what we also do in the paper is, in this case, provide a map of just looking at how things vary across different orders of effects, and so, or effects across orders, I should say, and looking at here just what happens when you have a shock in Bolivia, and how that spills over to the other countries. You can see here on the third map the feedback effects and all that. So, but basically what we're doing is here using this toy example, which is obviously underdeveloped, underspecified, but as a way of suggesting you can use mapping, and that need not be geographic mapping, to show how things play out across orders and effects. And here we do something similar using the SLX profile. I'm not going to spend a ton of time on this table because our time's getting short, but then what you can also do is looking at here we got Bolivia on top, but the other countries down below, just using the South American data and the Freedom House scores and the wealth information, and looking at how the spatial profile varies for each country with different types of heterogeneity across the different orders of neighbors of Bolivia. And then here, this is one that's in the supplemental appendix of this paper in PSRM, but basically building in what would happen in this case if you saw a 10-point shift in the DRC democracy score, what would happen to neighbors and on their effects. And so basically building in a simulated way of doing that. Okay, so as I wrap up here, I'll just say a couple of places we plan to go with this. So we're certainly making a call for the simplicity of the SLX model when appropriate, especially if researchers don't have a good idea of what the spatial process is. That might be a good place to start. If you have a great idea of a global process or a process that works through multiple mechanisms, then by all means start there. But of course, by all means, do the work that it takes to interpret those models appropriately. From here, though, we're going to go into looking at time and space together. So we're starting that again in the JLP article. You can see kind of a look ahead to that in the supplemental materials, but we're sort of looking at that at a basic level. We're getting much more complex now with a whole bunch of different spatial and time and temporal specifications together to see how things play out over time and space, and the ways of estimating those models and getting meaningful interpretations. Because again, whatever complexity you've noticed here, it compounds obviously much greater when you include temporal effects. And then some additional ideas about how we might do interpretation is something we batted around with as well. So that's where we might go. So otherwise, I'm looking forward to discussing anything folks have, and any questions, comments, and if you're interested in something a little deeper, happy to go back there and spend time if interested.
Okay, thank you, Cameron, for that presentation. At this point, Cameron Wimpy is available to take questions from the audience, and you can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will read your question during the Q&A period. And I must say, we've accumulated quite a few questions during your talk, so I'm just going to try to start with those and engage them. So the first question was asked by Michael Coppage. He'd like to know, well, I guess it's more of a comment than a question, but we'll see. I question how much we need to worry about the higher order effects, the W squared matrices and so on, in spatial autoregression, given that rho is typically small and gets exponentially smaller with each spatial lag. So the longer spatial lags typically don't make much of a substantive difference.
Yeah, that's a fair point. And certainly, and I think it underscores the fact that in many cases, we estimate these models and rho is typically quite small, and the spatial dependence is not something that is perhaps as large as what a theory might suggest. And so I think it's a fair point in terms of thinking about that part of it. Now, whether or not we should be completely or not be concerned with it at all, I think it's a different question. And I think it probably just depends on that degree of spatial dependence. It's something that where there's a lot of dependence and you might see a higher rho value, that might be something to consider. And certainly depending on what you're concerned about with respect to those things about spatial heterogeneity I talked about in terms of specifying different weights matrices and what that might look like in a Sar model, and the rho values relative to considering something where you have a bit more control over the specification process. But it's a fair point, certainly, and it's true that that's a diminishing process that plays out that is certainly worth thinking about. I mean, we're not trying to say it's the end of the world, but we are pointing out that it hasn't been acknowledged all that often.
Referring to the first slide with selected Monte Carlo results, and looking across the rows of that table, it looks like there's not a lot of variation. Why is this? And that question comes from Thomas Ball.
That's a good question. I don't know that I know why there's not a lot of variation across that, other than in many cases the recovery rate's quite good for what we were doing there. But it's a good question, I think, worth thinking more about. And it may be that one of my co-authors has an idea on that, but I'll think about it.
An anonymous attendee, I guess you can ask anonymous questions, but it's not, well, anyway. Can you provide a couple of substantive examples of second and third order spatial effects?
And to be clear, we're talking about true second and third order effects.
That is my interpretation of the question. Yeah.
Okay. Yeah. Well, certainly, like the easiest one that I might be able to think about is, and I'll say one thing first, preface that to me this is one of the reasons that the SLX is a nice case to make in the the spatial world, because in many cases we're only thinking about those first order effects and something happening locally, and we're not thinking about something that's happening further away to a neighbor of a neighbor. And so again, you rarely see that sort of elucidation in any sort of theoretical setup. And so I think it's worth pointing out that you're probably onto something either way. But I think you can imagine cases where, say, something 1994, something's happening in Rwanda that moves over into DRC that then involves Zambia. That could be, an example of that. But it's off the top of my head, it's not something you see a lot of, and it's not something we're not necessarily making a case that there's a ton of that out there. We're making a case that most of the spatial interactions that we see and that we're probably interested in as political scientists are those first order, those ones that are most nearby. And that's typically, I think, at least in my mindset, how we conceive of things, and certainly what you see in the literature. But if you're interested in something like that, or you have an example of something like that, you can still do it using the SLX framework. That's probably the best way to summarize that. Not to say that it's a really common thing, but that it's something you can do explicitly if you want to. It's also, last thing I'll say, because I want to make sure I don't take too much time, but it is sometimes you'll hear people talk about the Sar model, and they imply that they're capturing those second and third order effects, but they're really not. They're capturing those squared and cubed and so on down the line effects, and not true second and third order effects, which would take a different specification altogether.
I can give you another example. I think that would be appropriate. There used to be, I don't know if they're not studying it anymore or if I just moved on. But when I was in graduate school, I spent some time studying policy diffusion, which was something that my advisor, Bill Berry, was really interested in, and in particular, welfare competition. And among American states. And that's something where I think you would genuinely be looking for second and third order effects, because if one state raises its welfare benefits, that could cause reactions in other states, which then in turn causes reactions in other states. You can think of other policies like that. You can think of maybe abortion policies, which had some kind of spatial component in spread. You could think of... so there are lots of examples in states, I think.
I'll just say, Justin, I'm sorry. I was, to be clear, I was thinking about a situation in which you might want to directly specify this is happening in a neighbor of a neighbor or in a neighbor of a neighbor of a neighbor, specifically, like at that, at that fine-tuned second and third order level, versus kind of what you might also be describing, which is, a state adopts a policy and it spreads to other states. And by virtue of that spread, it ends up being a second and third order effect, for sure.
Well, with there's going to be, for example, because what you're mentioning is similar to what happens in just standard AR time series models, where there's a long-term effect and a short-term effect, right? Welfare competition, where the generosity of welfare is a continuous variable. You could imagine, okay, there's an initial, if there's some change, right, that has an initial, some exogenous shock causes an initial change in some state. Then that change in Y propagates to its immediate neighbors, which then propagates to neighbors of neighbors, and so on. That really is a second or third order effect. And you could actually make a similar case about learning, policy diffusion or learning. But whatever, we don't need to.
Right.
We don't need to spend 10 minutes talking about that. Thomas had a couple of other questions. You referred to the diffusion of democracy in your final spatial frontier paper. Would you elaborate on how that model was specified? For example, what was the time frame, years, decades, centuries? What were the geographic limitations or structure, and so on?
Sure, yeah, that was just South America, just 1994. Again, keeping it fairly simple. And you almost, it's one of those things where there's the desire to have an applied example, but also the desire to have an applied example that's not too complex, and that's one of the challenges I would just add of methods papers like this, where you want to have an applied example, or maybe even reviewers ask for an applied example, is you end up shifting it from a methods paper to a paper about that applied example, or at least dealing with that balancing act. And so we were able here to keep it just 1994, just for South America, and keep it as simple as possible as an example, of using that particular data set.
Well, he follows up and asks, how was diffusion developed or theorized?
Yeah, so I mean, this kind of a classic idea that as countries become richer, they, in terms of the internal aspects, but that basically it builds an example from Gledish and Ward in their 2008 little Sage book. Just again, looking at, democracy diffuses. We weren't necessarily theorizing how democracy diffuses so much as just saying this is something that's thrown out there all the time, that it's something that diffuses, and that was the example they started with in their book. And so we're not, again, it's same thing I said about the defense burdens applied example. It's not trying to say this is the end all be all for that literature substantively at all. It's just an example using applied data of how that process might work.
Well, that's interesting, because there seems to be a little bit of a tension between that and the idea that you introduced at the very beginning of your talk, which is that theory should dictate the structure of W and more generally the structure of the model, right? So the choice you make in how to model diffusion of democracy has to be wrapped up in some way in the process by which you think it spreads, right? So I guess one way of asking this question is, what sorts of spread are ruled in or ruled out by the model you chose? You're absolutely right. The other challenge there is certainly we're using geographic contiguity. That's also the example that they used in 2008. It's unclear whether democracy spreads across geographic boundaries physically, or whether it's, as you were just talking about, diffusion mechanisms, whether it's something that a country in a similar situation with a similar profile could say, this is what's happening there. Space means a lot of things.
Yeah. And so again, the basis of that was trying to make an example that was as real world as possible, but on the interpretation side, and that's certainly, that part is in the interpretation paper. But I understand the point in terms of that.
So I want to get to a question from Andrei Zhirnov. To what extent should we worry about spatial dependence due to omitted variables if we choose the SLX model?
Well, it could be a concern if you especially if you have a strongly dependent SAR process, and I think you see that in the Monte Carlo results to some degree. But going back to the earlier question, that's most often what we see the least. So most often we see strong first order relationships, which are going to be captured by the SLX if you've theorized the proper spatial diffusion mechanism in that case. Some independent variable in one unit is affecting the outcome in another unit, and the process by which that happens, which of course is what we were just talking about, how you might do that. But if you've captured that process, I'm not too sure to what extent you should be concerned about omitted variable bias with respect to spatial variables. Now, any omitted variable bias with respect to what you would normally think about for any type of study that you're doing, still going to apply, because in that case you're looking at a model of something happening in YI, using things from YI as predictors, but also something from YJ or another neighbor as well as a predictor. So the omitted variable bias could still be there for the within unit effects. In terms of spatial effects, if you've captured the spatial process with that spatial X model, I don't think you need to be too concerned. If you're thinking about other types of residual spatial effects that might be out there from, say, a broader SAR process rather than the SLX process, again, short of the situation in which you have a really, really strong SAR process, in which case your theory is probably off. You should have been theorizing globally and estimating the SAR in the first place.
We have a question from Cecile Richetta. I hope I pronounced that correctly. Thanks for the great presentation. Would using an inverse distance W change anything substantial in the interpretation of the results compared to first, second, and third order effects?
It's a good question. We played with a number of spatial weight specifications, and you can find them, all the matrices we used in our replication data. And so the short answer is I don't think so. We were using here the simple matrices just for, exposition purposes. Again, trying to make it as accessible as possible, because it's much easier to imagine a contiguity situation than it is a distance situation. And obviously, for those that don't know, that's inverted to account for closer things having more effect than further away things. But no, I don't think you'd see much difference. And I think you could, everything we've said, I would just say probably applies the same way.
I'm going to abuse my moderator's privilege and ask a question that I'm interested in. So, sorry, Thomas, I'm jumping the line. I'm really interested in thinking about treating the specification as an empirical question as much as a theoretical one, right? There's not a lot in your presentation about comparative model specification testing, right? So, if we're not sure whether SAR or SARX is more appropriate, why don't we run them both and then, compare them with some model fit metric or cross validation or something. To what extent do you think that specification of a model, sort of the choices that you're thinking about in these papers in this presentation, can be an empirical question, and if it is, how could you approach that?
Yeah, so it's a great question, and there's a couple of places. Number one, to look for sort of nods to that approach, and certainly David Darmafal's Cambridge book from a few years ago is a place where he's talking about Lagrange multiplier test, sort of similar process that you might use in other frameworks that aren't spatial. And certainly Scott Cook and Ralph Frances and Jude Hayes have done, at least presented this as a potential approach of having a more of a testing down type of scenario like you might in a time series world. And so we talk about that in the end of the JLP paper as a potential approach to this. Certainly if you have a theory about a fairly broad spatial process, we think that's a good approach, for sure. Or you're totally unsure of what it might be. There's nothing wrong with that approach. The argument we're making in terms of starting simple and getting more complex rather than the other way around is just thinking about the theoretical problem there. It's really difficult to imagine a spatial process that involves identifiable spatial interactions like at every level of in the outcomes, in the observables, and the unobservables, and so on. And certainly that's that general nesting model that was the first model in that taxonomy. But it's in practice probably weakly identified. And that's what they point out in their paper as well. And so then it's which model do you start from? Maybe it's the one that includes interactions in the outcomes and observables. So the SAR with the spatial X added on, that Durbin framework, and testing down from there. But so in addition to the theoretical aspects of this, most people thinking about first order theories in a fairly simple spatial process, there's also the complexity of estimating those models. And for the applied researcher, the software is not there to just plug and play that process. It's quite challenging to do that. And so I would say those are the immediate hurdles, but in addition to theory being your guide. But it's certainly, I wouldn't say it's a competing framework, but it's certainly an alternative approach that we're not opposed to by any means, but it's a difficult place to get to, I think, for a lot of applied researchers.
I would be curious to know, not that you need more to do, but I would be curious to know, first of all, whether AIC, BIC statistics that are fairly easy, quote unquote, to compute as long as you have a likelihood value, would be effective at discriminating between these models.
Mhm.
And also whether, how exactly you'd write down the AIC and BIC, because of course the number of parameters in the model is a key variable there. But in this case, we're really comparing different spatial matrices, and that's a little different than a parameter estimate. Well, we're out of time. I want to, first of all, if you asked a question, the Zoom keeps a log of all these questions, so I will send them to Cameron, so he will get all the questions that we couldn't get to. I'm delighted we had such an active discussion. I want to thank Cameron for being here today, and I also want to advertise our upcoming talk. So on April 2nd, we're going to host a talk by Pedro Rodriguez of Vanderbilt University. Please see our website, www.methods-colloquium.com, to get more information about this talk. Cameron, this was great. Thanks very much for being here today.
Thanks, Justin. Thank you, everyone, for coming, and thanks for all the questions.